We were asked to be provocative, so I figured I'd stimulate thoughts with at least a somewhat provocative title. I think that I've been asked to speak about how AI might affect how we do science and our jobs in science. And I think the reaction, at least many of my colleagues have, to something like that is very similar to the reaction they have now to the US presidential election. It's either overwhelming anxiety or it's roll of eyes, and I really, really don't want to think about that right now. I'm a little bit, more hopeful for the future, perhaps irrationally so. And so I'd like to talk to you about a few thoughts of the future, the near future, and the more distant future. But in thinking about the future, it always helps to think about the past and what history might have told us. And for those of you who are alive, like me, during the early 90s, you might think back to that moment in history and the presence of the future when you looked on your computer screen and opened that browser for the first time and gazed through that portal at this thing called the internet. I think we're at a similar junction where the revolution is coming, and we can either brace ourselves and participate or be swept away. So that's probably the strongest statement I'm going to make today. Turing, however, back in 1950 in the journal Mind, published the paper Computing, Machinery, and Intelligence. And in it, he said, in about 50 years' time, he was a little early, it will be possible to program computers to make them play the imitation game so well that an average interrogator will not have more than a 70% chance of making the right identification after 5 minutes of questioning. So that's how we think about the original Turing test as posed by Turing. Can you have a chat and tell the difference between a person and a computer, say over a 5-minute period? And well, as you now know, things are pretty close to that. In controlled trials with controlled evaluators, ChatGPT will now fool people in over about 2 minutes, about 60% of the time. So I'm going to give that a tentative check mark as the original Turing test being passed. But of course, there are always moving goalposts as people see one test being passed. So Peter Allen has always had the vision of creating a digital Aristotle, and he formed an institute to try to push progress along, and they came up with another Turing test, which was to have the system pass an 8th grade multiple choice test. And those of you who are in the US and have 8th graders might not be very impressed by this. But in 2015, the code failed. It got a D-, about 60%. But since that time, the results have been pretty spectacular. ChatGPT-4 has scored 86% on a whole range of college-level multiple choice examinations. There are other benchmarks for how agents, like people and others, can use the internet and shop and do the types of things we do when we browse. And systems can now do that and be highly successful as well. So again, the goalposts have moved and moved a lot. The bar has gotten a lot higher. And people are now considering the possibility of potentially awarding a Nobel Prize someday to an AI system, discovery in science. So Catano came up with the idea of the Nobel Prize Turing Challenge, where by 2050, the community is challenged to develop a system that can reason like a scientist, meaning analyze data, generate hypotheses, design experiments to test those hypotheses and interpret the results. Well, that's a big leap. And of course, in all of these Turing tests, the premise is that humans are intelligent, and anything that imitates humans spectacularly well can therefore be considered intelligent. But of course, we could imagine that AI systems would have a different kind of intelligence. In fact, you might think of intelligence as broadly defined as being able to conduct efficiently and successfully a broad array of tasks under very different environmental conditions. But at any rate, it's worth asking ourselves, do we actually want digital Aristotles? Do we want to end up, clerks that check the work of our digital masters? I wouldn't want to be that, but it seems like we are rapidly moving in the direction of embracing the possibilities. Here's a plot just from the period 1985 to 2022, representing the engagement across 20 scientific fields, including physics and astronomy, in AI, in papers that mention machine learning or some kind of form of artificial intelligence. And this engagement, while it's increased in papers by over 13-fold, is also interesting because the fraction of papers in every one of those fields has increased dramatically as well. So you've all heard about AlphaFold, which was a rather remarkable solution to a very long-standing question, whereby people wondered whether or not sequences of amino acids could be used to predict the origami-like three-dimensional structure of the protein that they would make. And a lot of money had been invested, a lot of effort had been invested in that. And it was a problem for which, the possibility of a solution was known, but the form of the solution was not, and there was lots of data. So in many respects, that was a glorious use case for industry partners because there was also a huge upside with regard to its impact on medicine and the like. And AlphaFold 3 is now, in 2024, looking at biomolecules like ligands, which are very important, small molecules important for the drug industry, DNA, RNA training, very interesting. And there's also been similar successes with regard to constraining plasma in tokamaks, which, again, most of you know is a very long-standing problem in actually keeping the plasma in check with magnetic coils. Remarkable work that has now optimized the control of the plasma through these magnetic coils. It was trained on simulations. There's simulations iteratively, in real time, experimented with different control strategies, developed policies to contain the plasma over different geometries, and when applied to a real-life tokamak, actually was successful in predicting and controlling the magnetic field. So a lot of potential there for fusion experiments. And in astronomy, we've heard all week, fascinating talks, and there has been a few mentions of machine learning and artificial intelligence applications. As you all know, the decadal survey in the US had hundreds and hundreds of pages and 1.5 pages on AI and machine learning. I think that's going to change. In our own department at the University of Arizona, we're doing a host of things similar to, for example, what Risa mentioned, looking at the connection between galaxy formation and dark matter, gravitational lensing, various other things, but also working on finding rare astronomical transients, directly imaging black hole accretion with the Event Horizon Telescope, seeing further into the cores of galaxies, understanding how stars form from molecular clouds, automating the localization and the follow-up gravitational wave sources. And there's a lot of interest, following up on Sarah's talk, in detecting and directly imaging Earth 2.0. So another thing that people are investigating is improving instruments and telescopes and using AI in various capacities to improve adaptive optics and other kinds of alignment techniques. So, for example, in our own department, there's work actually being done correcting nonlinear wavefront sensors. There are wavefront sensors that are quite sensitive, like pyramid wavefront sensors, that nevertheless have a nonlinear response to any kind of aberrations in phase. And it's a real problem for coronagraphs generally. But using neural nets, you can see what's been produced on the left. For imagery construction, you can do a lot better. But another problem when you're looking at coronography is turbulence, atmospheric turbulence, and correcting for that, because that will create deformations in the incoming wavefront. So you can see in the lower left that there's also been success, again, using this kind of reinforcement learning that was used for the plasma control experiment, feeding actions to the environment, at least in the lab, observing the outcome. The code is observing the outcome, and the code is improving its strategy and developing a policy based on a stipulated reward, which can be some figure of merit to achieve with regard to some contrast that the coronagraph is sensitive to, and that dramatically can improve the ability of coronagraphs to function. And finally, maybe a more pedestrian problem on its surface is this issue of getting your telescope to point straight, right? Or getting it to track well. Now, this is not necessarily a big problem for the most expensive telescopes in the world, but it's actually a problem for a lot of middle size and smaller telescopes, and it wastes in aggregate an incredible amount of telescope time. And so if you can actually, and this is the WIN telescope pictured here, 10% of the targets initially fall outside the pointing field, and people are sitting there actually manually maneuvering the target into the slit or into place in the image. And you can build models that will actually create much better efficiency in the telescopes. And that, even if you don't care about smaller telescopes, translates also into big improvements potentially in alignments of multi-mirror telescopes like the ELTs, and even systems like this on the right, which is being prototyped at Arizona, which is going to consist of thousands of off-the-shelf telescopes connected by optical fibers to a high-resolution spectrograph, and hopefully in the end create an aperture that's about 20,000 square meters. And alignment is a serious issue there, which neural nets can help with. All right, so what are some of the grand challenges that we're facing beyond the work that's currently being done? And a study from the National Academy of Sciences has come up with a few main categories. One is exploration and mining of the literature, the entire corpus of literature. For example, you could imagine a challenge whereby if the corpus is seeded with synthetic papers that have hidden discoveries in them, can a system identify the paper that contradicts the majority sediment? Another idea is, as we mentioned earlier, a key to getting that Nobel Prize-winning AI system is the formulation of general hypotheses. And there are challenges here whereby you could imagine in a simulated experimental environment, can an autonomous agent identify why simulated researchers say are getting sick? Any challenge has to have clear, automated metrics, graduated passing levels, you give people hope, and long lead and competition time so people can put the work and effort in to do it. And another aspect of all this that ties it together is AI-related and enhanced computational infrastructure. And this is something that hasn't received a lot of attention, but innovating in the computational infrastructure is absolutely essential to making everything else work. And what do I mean by that? Well, let me show you a demo of a prototype we've worked up at Arizona at MIT. This was done by an MIT student named Zui Chen. Our colleagues in computer science at MIT and the University of Arizona have come up with a system called palimpsest, which is quite extraordinary. A programmer can give it a very sophisticated but high-level set of instructions or a prompt, and it will create a bunch of codes to then find what models it needs to most efficiently solve the problem. And in this particular use case, it's being used to generate a search of the astronomical literature. Now, ADS, Archive, even Google are wonderful tools, but you've all had the experience, I'm sure, where you really needed to look something up, and you type in the question and you get a bunch of link salad. And you have to, or reasonably your graduate student has to go and click through every one of those paper links and try to figure out where the answer is. Should we be settling for this in the age of such sophisticated capabilities? I don't think so, so here's the demo.
This is the demo of AstroDB, which allows searching information in astronomy papers. If you want to know the halo mass of the Large Magellanic Cloud using Google or ADS, it only gives you a list of papers. While in AstroDB, we directly give you the answers with links to the source. First, let's pre-process the source containing 500 PDF papers about the LMC. The pre-processing includes downloading the PDFs, converting them to texts, and then build a search index over the texts. After the pre-process, we can now quickly search for any attributes in these 500 papers. Let's search for halo mass. Unlike Google or ADS, AstroDB directly produces a table, with each row containing a value, and the source paper the value comes from. If the value is cited from another paper, the citation is also noted. Furthermore, each source paper is then highlighted, so one can click into the paper and quickly find the context the value is extracted from. After checking the context, we can confirm that the extracted 1.5 times 10 to the 11 solar mass is indeed correct according to this particular paper. Then we can provide feedback on the quality of extraction to help AstroDB improve search results in the future.
Why not? Now, I'm sure you're coming up with lots of cool things that you can do with this. Did they ever plot my favorite X versus Y? Can I extract all the X's? Can I extract all the Y's and have it create a graph for me? Sure, why not? Did so-and-so actually say that in their paper? So there are lots of potentials here. And I think it's something that you could see your way towards actually using. Because of the infrastructure on which it's built, there's a tremendous opportunity for data collection and curation. There's a tremendous opportunity for the AI enhancement of astrophysical pipelines, because this system will build codes to do whatever the higher level task was required to do and optimize it. Let's talk for a moment about that other grand challenge I mentioned, which also has to be built upon AI-enhanced infrastructure, generating hypotheses. And Ofer Lahav had a very nice discussion of this in his talk, but I'll go over it again because it's very compelling, at least to me. Imagine in the case of what I just showed you, AstroDB, you have the entire corpus of the astronomical literature at your disposal. Imagine then that you could read all the correlations off the graphs or out of the tables, or even any mention that an individual made, like, this drives that, this is caused by that, this could be the confounding variable for that. Well, the field of causal AI combined with that kind of literature search together can really dramatically affect what you're capable of doing. In fact, you could, if you're interested in giant planet formation, for example, have it search the literature, identify, in this case, it's oversimplified, a few variables, the star's mass and the star's metallicity, that may affect the formation of the giant planet. But then, reading all that information from the paper, it will synthesize it into potential hypotheses. So for example, one hypothesis might be that the star mass and the metallicity both drive giant planet formation. Or you could have a class of other hypotheses that are more like a chain, where the star's mass, in fact, drives the metallicity, which drives the giant planet formation. Or you could even imagine that some of these arrows are reversed in the other way. But the code will ask questions. For example, is the star mass and the star metallicity correlated with each other only when the giant planet is present? That would tell you that the first hypothesis is valid, that both drive it, and that the second hypothesis to the right can't be true. Or you could ask whether or not the star mass and giant planet formation are only correlated up until metallicity are controlled for. That would suggest a whole second class of hypotheses as being possible. Now, you can imagine which way this is going, even though this is simplified. You could take the corpus of the astronomical literature, identify as many variables as you want, use the logic of the graph to build up relationships that show causal relationships. So, for example, you might find out that age, in fact, is what's driving both star mass and stellar metallicity. The point to this methodology is you're taking what people have already stated in literature or suggested, you're visualizing it in a structure that provides this kind of natural explainability and gives you directions in which to go. No one would publish this, but you would use this as a guide to which hypotheses may be new, which hypotheses could be verified, which could be falsified. And you'd see it all in its beauty in multidimensional space. So what's next? Well, there are a lot of things we can envision before we get together, or at least some of you get together for the next celebration here. One is that telescope systems, we talk about roboticized telescopes, but we don't really have roboticized telescopes yet. But there should be roboticized telescope systems that communicate and strategize with each other, reduce the data, and tell us when more data is needed. We can envision that that is a possibility, be particularly helpful for the coming onslaught of astrophysical transients and gravitational wave sources. We can envision, along the lines of something I mentioned earlier, automated data collation, curation, visualization, and even exploration for relationships through that type of causal AI idea. This I'm very intrigued by. English does not have to be the language of science anymore. We all have Zoom. There's nothing to prevent us from having a Zoom conversation with anyone in the world in any capacity with simultaneous translation of the language. The options for collaboration and access are just going to balloon. Likewise, we can imagine collaborations with creative people, but in other domains who may not have more of the traditional training that we've come to expect because of the ability of particularly natural language processing and these large language models to translate trivially, as I'm sure you have all experienced, from the language from one domain to another. Access to the discovery space is going to broaden, hopefully a lot more for those outside the most privileged and absolutely exquisitely lovely institutions. And my personal favorite, we're going to be doing a lot less grading, but of course our students are going to be doing a lot less working. And I definitely think this is a comment made by Veloso, again in the National Academy of Sciences report. Human AI collaborations are going to be the most effective. You could imagine that balance changing over time, where AI could examine problems, decide whether it can solve them, and if not, pass it along to us, where it will record our solution, and over time, learn from our solution, and take over more of the responsibilities, freeing us to do the more complex problems. So, finishing up, we started with the idea, well, could AI be a partner? Could it even be a Nobel Prize-winning scientist? You know, if human imitation equals intelligence, then we need to figure out how to formalize scientific discovery, all those steps in the process. That's a tough nut, but people are thinking about it. Or we do something similar to the polymathic AI group, Shelley Ho and Miles Cranmer, who's here at Cambridge, are doing, is just pre-train everything out of a huge corpus of scientific literature, and then fine-tune for specific tasks, much as language and vision models operate today, where you pre-train on a ton of paintings and images, and then you fine-tune later for a particular style of painting. maybe you fine tune on the greatest discovery papers ever made. But AI is different. Its intelligence is going to be different. But that doesn't mean it can't surprise us. And in fact, Turing had this, well, sort of debate with Ada Lovelace. So Ada Lovelace had said that she did not believe the so-called analytic engine of Babbage could ever produce anything original, could ever generate original thought. And Turing said that her objection boiled down to just computers surprise us. And he said, where the consequences of different facts are not immediately recognizable, it can surprise us. And that's this idea that there are connections, even in the data, even as limited as the data effectively are, in those data that we haven't made, that it may connect. And it specializes in all disciplines, and it finds links across all scholarly languages. Well, one problem, and I've got one more minute, Carlos, I promise. In thinking about whether it will recognize a discovery, we have to worry about whether its scientific taste is going to be as horrific as its artistic taste. I asked for a prompt, what would it look like for a scientist to be in partnership with AI? And this is what I got. And this suggests the big, deeper issue of the fact that there's a real regression to the mean. You know, these are distributions that are being interpolated, and you really want to push in your prompts the AI to sample the tails of those distributions, to try to find the unusual, the rare concepts in training. And there are a variety of ways, and people are pursuing that problem. So let's get rid of this. I don't know why. The robots are always portrayed as taller. It's really... We know we want limits, though. We want the AI for the busy work, maybe suggesting directions, but leaving the real discoveries to us. How do we thread that needle? And what's going to be okay when AI starts being able to write good papers, not lousy ones like it does now, or write proposals or talks, or even supervising students? And very importantly, and this is an issue brought up by Miles Cranmer in a recent talk he had, you know, how do we interest computer scientists and industry people in our problems? They were interested in AlphaFold because they saw this tremendous monetizable and visible payoff. How do we interest them in our data? They keep training on, you know, zip codes and people's addresses. Why don't we get them to train on LSST? Right? So, good questions for the discussion. Thank you very much.
Thank you very much.